As we study analytical trigonometry, we first are going to be using these fundamental identities. Now, some of these we've already talked about before. For example, the reciprocal identities are ones that we have already looked at, and we've graphed each of those to see what the graphs look like. We've also talked about tangent and cotangent in terms of sine and cosine. We'd refer to those as our quotient identities. And then we've also talked about the Pythagorean identities. We will use these more within this next lesson. And remember, the sine squared plus cosine squared equals 1. That comes from, obviously, the Pythagorean theorem and our unit circle. Now, as far as these other two, well, if I divide this first Pythagorean identity by cosine squared theta, that's where the second Pythagorean identity comes from. And if I divide my original by sine squared theta, that's where we get our third Pythagorean identity. We also have these cofunction identities. A cofunction, like sine and cosine, are considered cofunctions. And what these identities are really saying about these cofunctions is that the complementary angles, which this is 90 minus whatever our angle is, that these complementary angles, if I look at the sine of an angle and the cosine of its complement, that they are equal to each other. Then we have cosecant and secant, which are considered cofunctions, and then tangent and cotangent. Now, another way that we could write this down is we could basically say here that we know that the sine of 30 degrees would be equal to the cosine, because those are cofunctions, and then the complementary angle to this, which would be 60 degrees. And that's stuff that we've seen on our unit circle. We could say the same thing then for any set of complementary angles. For example, 70 degrees. Tangent of 70 would be equal to, our cofunction would be cotangent, and then the complementary angle would be 20 degrees. Or we could take secant of 40 degrees, and that would be equal to the cosecant of 50 degrees. Now, we've talked about this, and what you're basically doing is you're switching the angles within your right triangle, and so what that does is it switches your opposite and adjacent sides. And so we have already referred to these being equal in that aspect, but here's our identity, and those are known as the cofunction identities that go along with that. The other thing that we have, remember we talked about even and odd functions previously, and to be an odd function, if you plug in the opposite of x, you get the opposite of that value back. That would make that an odd function. Now, if you plug in the opposite of x and get the original back, that's what we referred to as an even function. And we did this early on when we were looking at, for example, cubics. Those were odd, whereas a parabola was giving us an even function. Well, it turns out that our sine and tangent and the cosecant and the cotangent are all odd, whereas cosine and secant are even functions. And so we have those identities that we will use as well. First example, we're going to use the given values to determine all 6 trigonometric values. And remember, we've done problems like this before, and the first thing we did was we drew ourselves a triangle. And so we know that sine is positive, and remember that's when we're going up, and secant is also positive. Secant, we're going to the right, so where these both happen would be in quadrant 1. So we're going to draw ourselves a triangle in quadrant 1. And so here's my angle theta. That means that if I know my sine value is equal to, my secant is equal to 4, then that also tells me that my cosine would be equal to the reciprocal, which is 1 over 4. So then 1 over 4 gives me an adjacent side of 1, and our hypotenuse is 4. I can then use the Pythagorean theorem to find my third side, which would be the square root of 15. We'll just leave that as a radical, because if we're looking for exact values, square root of 15 is an irrational number. That would be our exact value. So now as far as finding the sine of theta, now we have opposite over hypotenuse, so we can now use the triangle to find the rest of these values. The reciprocal of that then would be 4 over the square root of 15. We, of course, want to rationalize our denominator, so that would be 4 square root 15 over 15. And then as far as the tangent is opposite over adjacent, That would be equal to the square root of 15. The reciprocal of that would be 1 over the square root of 15. Again, rationalizing the denominator would be square root of 15 over 15 for that value. Example, we're going to use our fundamental identities to simplify this given expression. Now, anytime I see a squared, I think of the Pythagorean identities. And one thing that I notice with this one is that we do have a secant squared, and we have a couple of sine squareds. If there's a way I can maybe separate that, for example, if I can factor out that sine squared x, in this first term I have one of them here, and then I have that sine squared times the secant squared, and then I have another sine squared here, which I'm going to factor out, and so that would be a minus 1. So then going back to our Pythagorean identities, here's a secant squared, and we have that's equal to 1 plus tangent squared theta. Now we can rearrange this a little bit. So if I know that, for example, 1 plus tangent squared theta is equal to secant squared theta, well, to get secant squared minus 1, I could subtract 1 from both sides, and this is going to remain equal. So then that would give us tangent squared theta is equal to secant squared theta minus 1, which is what we have right here. So then I could sub that in for that piece, and so what we end up as far as simplifying goes is we have a sine squared times a tangent squared. And as far as simplifying, there's really not much more that we could do from there. That would be a simpler expression. We're still using our fundamental identities to simplify expressions here in this next example. And here we have a cotangent cubed x plus cotangent squared x plus cotangent of x plus 1. Now we've already solved problems similar to this here, where we had something like x cubed plus x squared plus x plus 1. In which case, something where we start off with a cubic and we have these 4 terms like this, what we talked about doing previously is to factor by grouping. So we'll still follow all of those same rules when simplifying these expressions. For example, when I look at these first 2 terms here, I see that I have a cotangent squared in both of them, so that would be the common factor if we're going to factor by grouping. So I'll take a cotangent squared x out of each of those. Now I take one out of here, and we still have another cotangent of x. And when I take one out of here, that leaves us with just one. So factoring out that cotangent squared x out of the first 2, we have cotangent of x plus 1. And then as far as out of these 2, I could factor out, looks like just a 1 on that. And then I can take 1 times our cotangent of x plus 1. Remember, the whole idea when you're factoring by grouping is that you want to have these 2 quantities be the same. So when you're taking out your factors, remember to have that group be the same on each of those, because then we put these pieces together, and that's one quantity, cotangent squared of x plus 1. And then our other quantity is this piece, cotangent of x plus 1. Oh, I see a cotangent squared. So again, I think about my Pythagorean identities. We have cotangent squared theta here. If I subtract that 1 over, then I can see that that would be, it's equal to cotangent squared theta plus 1. So that's equal to cosecant squared theta for that quantity. And then here we still have, not able to simplify this one at all. Just leave it as cotangent of x plus 1. Example, we're going to factor the expression. And again, we've done problems similar to this as well. We could think of this as 6x squared plus 5x minus 6. And just treat these as our variables. And we're doing the same thing. So in factoring this, it's the same idea for each of these. And we would be able to factor this as 3 cosine x minus 2 times 2 cosine x plus 3. So remember, here we're looking at our first terms multiplied to give us our 6 cosine squared, and then our last 2 terms, a negative 2 and a plus 3, give us our negative 6. And then if we look at the outside and the inside, we have the plus 9 and the minus 4. That's what gives us our middle term there. In this example, we're using our fundamental identities to simplify the expression. And when I see our pi over 2 minus x here, makes me think of our cofunction identities. And we had already said that cosine of pi over 2 minus theta would be equal to the sine of theta. So as far as simplifying this goes, we could write these in terms of the same angle. That's one thing that we're going to want to be able to do, is write these in terms of the same angle. So we know that the cosine of this angle would be equal to the sine of x. And the other thing, as far as simplifying goes, I'll typically take something like secant or cosecant, sometimes even our tangent and cotangent, and write them in terms of either sine or cosine. Now secant we know is equal to, as far as our reciprocal identity goes, 1 over cosine. So now we have sine of x times the 1 over cosine of x. That is sine of x over the cosine of x. And as far as simplifying that goes, that is equal to the tangent of x. Last example, we're asked to subtract the two and then use our fundamental identities to simplify. And to be able to subtract fractions, first thing we would have to have is a common denominator. So in that case, I would need to take this fraction where we have secant of x plus 1 for our denominator and multiply it by our denominator here, secant of x minus 1. We're going to do that on top and bottom, multiplying those quantities. And doing the same thing on this side, we have our fraction 1 over secant of x minus 1. And again, to get that common denominator, I'm going to multiply top and bottom by secant of x plus 1. So then on top here, it's 1 times the quantity. We end up with a secant of x minus 1. And here we're going to have a negative 1 times that quantity. So we're subtracting the quantity of secant of x plus 1 on this side. And then as far as our denominator goes, well, if you'll notice, we have a minus 1 and a plus 1. So that's going to turn that into secant squared of x minus 1. It would be difference of squares. Now, as I distribute this negative sign, we end up with secant of x minus 1 minus the secant of x minus 1. Still all over secant squared x minus 1. So we have a secant of x, that's a c, secant of x minus 1, and here's minus secant of x. So those cancel each other out. We have a negative 1 minus 1, so that would be equal to negative 2 for our numerator. And then secant squared x minus 1. Anytime I see a squared, I think about our Pythagorean identities. So secant squared is there. If I subtract the 1 over, then that would be equal to tangent squared. To have tangent squared theta for our denominator is simpler. So we could stop here and have that as an answer. If we want to get rid of the fraction, we do know that our reciprocal, we could use our reciprocal identity and also write this as negative 2 times the cotangent squared of theta. And that would be also another simpler way. There's more than one spot we can stop along the way on these.